So a few months ago I found this in my neighbor's trash. This 40-pound mechanical masterpiece is the IBM Selectric II, an electric typewriter released in the early 70's. The Selectrics are well known for their weird golf ball-like typing element. See, on a regular typewriter, what you got to type with was pretty much limited to whatever was molded into the hammers. But with the Selectric, you can change out what font you're typing with just this quickly. And with only one typing element, your keys can never get stuck with two hammers like this. In fact, you can hold down multiple keys and it will still type. Finally, you might think you're satisfied with the speed at which you can type on a manual typewriter, but a Selectric is absolutely blazing fast. It's no surprise that after their introduction in the early 60's, the Selectrics eventually gained 75% of the market share of typewriters. They made millions of them, so many that this is actually the second one I found in the trash. The first one was actually when I was a kid. Although you can't expect a single-digit-year-old to fix one of these, I'm glad that almost 20 years later, I'll finally get a second chance. I even still have some of the parts, like these springs. So the first thing that was wrong was this little arm that pulls the ribbon along. It had seized up, so it was just a matter of taking off some gears and applying some oil. The second problem was something to do with the keyboard. There were a few keys that when you pressed them that just wouldn't type anything. So for that I ended up tearing apart the entire keyboard, and sure enough there were some bent parts making it not work. The problem has to do with something called the selector compensator. It's just a tube full of ball bearings, and when you push down a key it pushes a little tab into the ball bearings and takes up the slack. So there's enough room for one tab to go in, but not two tabs, so you can't push two keys down at once. Or at least not at the same time. So digging into the machine, we can sort of almost see in this picture the bent up compensator tube. Somehow one of the balls had popped out through the side of the tube, which is not supposed to happen. And to get to that, I had to tear down even more of the machine. And by this time, you're probably thinking, yeah, this is a bit complicated, isn't it? So it's as good a time as any to go over how the machine is actually supposed to work. So it all starts here with these comb-looking things. There's one under each key, and each one is cut differently, kind of like a house key. I guess it would be kind of silly to call these keys, so IBM calls them interposers. When you push a key on the keyboard, it pushes down one of the interposers, which in turn pushes on the cycle bail. That's the silver-colored bar at the top of the picture, which goes from left to right. The cycle bail trips a set of latches on the left side of the image, which trips a clutch located next to this drive pulley. That further engages a series of shafts and gears, including this paddle wheel looking thing, which pushes the interposer back up. And since the interposer was down to begin with, it pushes on the selector bails, which are the black rods going from left to right. That combination is then picked up by the latch interposers on the left side of the machine, which transfer the selection down these rods to the all-important wiffle tree mechanism. It lifts up these hooks to either engage or disengage the legs of the wiffle tree. Well, actually 5 of them do that. The 6th one just prevents this black bar from being pushed down, but it's also connected to the wiffle tree. But how does this motion make it up to the ball? After all, the carriage is allowed to move back and forth. This is actually one of the things I find most clever. To tilt the ball to the right character, it's mounted on a pulley, and then a loop of metal ribbon goes all the way from one end of the machine to the other. As long as the size of that loop stays the same, the carriage can move back and forth and the ball will maintain the same orientation. But if we change the size of the loop, the ball will rotate, allowing us to select a different character. There's another loop to control the tilt of the ball, up or down. And then the size of the loop is determined by these 2 pulleys, which are attached to the output of the wiffle tree, which is really just a series of levers that converts the selection into an amount of tilt on each one of these arms. Finally, a rotating shaft passing through the carriage, powered by that clutch from earlier, fires the ball towards the paper. And congratulations, we've just typed something. And all of this happens lightning fast, up to 15 times a second. When the Selectrics were introduced in the 60's, they pretty much doubled the average typing speed overnight. Now, of course, there are some things I left off. For instance, shifting. Now, when you type normally, you don't really shift all that often, so they took all the capital letters and put them on the other side of the ball. And whenever you push the shift key, it activates this cam to pull another arm on the right side of the machine, which changes the size of the loop by exactly a half turn of the ball. And then there's this whole other section on the right side of the machine with more levers and clutches and things like that to control the spacebar, backspace, carriage return, and new line functions. The back and forth motion of the carriage is also powered, of course, and this is probably my favorite mechanism in the whole machine. The shaft rotates all the time, and on the shaft there's a bunch of these things that look like springs, but you'll notice that the gears are not engaged with the shaft until we apply a little bit of friction to the end of the spring, which makes it tighten around the gear connecting it to the shaft. Very simple, very clever, and very repeatable. The entire typewriter is powered by only this small AC motor, and that clutch is there just in case you happen to power the machine up while something's already engaged. At low speed, the motor just doesn't have enough torque to overcome the mechanism. They really did think of everything, including this mechanism whose only purpose is to stop you typing a key while the carriage is either being tabbed or during a carriage return. So hopefully that wasn't a bad explanation, and you can further appreciate the over 2,000 mechanical parts that go into one of these things. That's what they say anyway. I didn't count mine. And really, what are you going to do with a typewriter in 2023 anyway? Sadly, the Selectrics and the electric typewriters in general just aren't really appreciated even by the hipster typewriter people. But for me, I'm more of a hipster old computer person. So I think I'll try to make my Selectric into a teletype. What is a teletype? Well, if a telephone lets you hear things remotely, a teletype will let you type things remotely. These were used for all sorts of things in the 20th century, mostly as a way to send documents from place to place, sort of like a precursor to the fax machine. By the beginning of the home computer revolution in the 70's, people were hacking up Selectrics to use as printers. This wasn't really a time where you could just go out and buy a desktop printer. They just didn't exist. And when they did eventually come around, they kind of sucked. Sure, the output from dot matrix printers is somewhat legible, but it's complete garbage when compared to the crisp printing that a Selectric can do. And while some hackers made adapters for their typewriters that look like this, the Selectric typewriter's unique selection methods enabled them to be converted to printers much easier using far fewer parts. Even Don Lancaster's TV typewriter book included instructions on how to convert a Selectric typewriter, although they didn't usually use the keyboard part as a keyboard. By that time, keyboards were a lot cheaper, and you could just buy one. Some companies produced fully converted Selectrics, others were available as a kit. And while the brochures for the kits are still around, and sometimes you'll find pictures of a kit, there aren't all that many typewriters I've found that actually use them, except for this one guy on Reddit. And of course, on the more professional side, IBM wasn't left out from hacking up their own machines, which were never intended to be anything but typewriters. The Selectric series was extended to fancier typewriters, which could remember lines or even whole pages of text, and could do special things like justified text. They even made this system which could record entire documents onto these magnetic sheets. This must have cost a fortune when it came out in the 60s or 70s. Also, it's kind of weird thinking about how much paper we used to use to operate a business. And IBM did make modified Selectrics to use as computer terminals, much like contemporary teletypes. They use them for IBM's own computers and other mini-computers, some with which you might be a little more familiar. These modified Selectrics were prime targets for conversion to a printer because they already had the solenoids needed to get them to type by themselves. But I'm not really sure where you'd find one of these machines even if you wanted one, unless you're willing to entertain insane eBay offerings. So we'll have to do it ourselves, and besides, mine was trash to begin with. So, armed with a few handfuls of cheap solenoids from AliExpress, I was off. And if you're following along at home, you can read my original drawings. Just kidding, all the 3D printed stuff I made for this is in the link in the description. Although some of these parts were modified after the fact, so I'm not sure how useful they will be to you. We'll start off with these fingers that were 3D printed to fit on the latch interposers. Now, these are just super glued on, and they won't damage the underlying metal in case I ever want to remove them. And then there's a 3D printed carrier to hold the 6 solenoids that actuate these fingers, and this is held on just with 2 screws that were already present in the machine. However, we still need something to initiate the cycle, and that's done with this small solenoid with a hook on it, just hooked onto the cycle bail, And that one mounts with 2 more screws into 2 more pre-existing threaded holes. There's really a lot of those on this machine, and I tried to use them wherever possible. Next up is the shift solenoid, which mounts to the side of the machine just like this. And this is actually the only part of the machine that has a modified piece, which is this push rod here. And the reason it's modified is just so I don't have to pull down the physical shift key, which is secured with some pretty hefty return springs on it. The push rod is just trimmed, and then I made this brass piece that slips over one side and soldered in place. So now the push rod can still push, but if I pull it with the solenoid, it doesn't pull down the shift key. Next is a carrier for 4 more solenoids that control the spacebar, backspace, carriage return, and new line functions, which are located on these 4 levers here. It's kind of an inconvenient spot to mount these, but there's really no better place to do so. The typewriter levers need to be pulled down, so I have these 4 rocker sets that convert the down motion into a back motion. And then 4 plastic blocks help hold the solenoid plungers in place. The better these are held in place, the closer they are into the solenoid, the harder they can pull and the faster they can react. You'll notice that the solenoid for the spacebar on the left is a bit out of the way, but luckily there's enough room to extend the rocker for that all the way over. Although the larger rocker and increased mass made things a little inconsistent, so I added a preload spring just to help smooth it out. With the case bottom in place, you can see how tight of a fit it is, but I did manage to achieve my goal of having the entire thing fit inside the original typewriter case. Finally, there's one more solenoid, and that's for the bell. Almost all teletypes had a bell on them that you could trigger with a command to make a bell ring, get the operator's attention, or for an error message, or whatever. So of course mine had to have that too. So there's the 13 solenoids required to get the Selectric printing. Much better than a solenoid for every key. But how about the keyboard? Considered by some to be the best feeling keyboard ever, and no doubt an inspiration to many of IBM's early computer keyboards. To monitor the keyboard, who better to ask than the Soviet Union, who in the 70's and 80's bugged the American Selectric typewriters in the embassy in Moscow. They did it by making nearly identical latch interposers that had magnets in the tips, and then using very well hidden circuitry inside the typewriter itself to monitor those magnets. The full article is definitely worth a read, and although I'm not using magnets in my version, I am going to use the exact same location, which is the tops of the interposers as they pass through this guide rail. I'm using opto interrupters in my version, although the ones I have will not all fit side by side, so I took them apart and made a custom 3D printed housing for them that fits over the rail. The Soviet version was incomplete. They couldn't read every single key on the keyboard. For instance, they couldn't read the combination when no interrupters were activated, which is a dash or an underscore, and they couldn't read space or enter or anything like that. Good enough for spying, but not for a computer terminal. So we'll have to add yet more interrupters. The first of which is this interrupter on the cycle latch, which activates before anything else whenever you hit a typed character. And then for the space, backspace, carriage return, and new line, there's these 4 fingers that are used to reset the levers. This bar pushes them up. And it's a perfect place to install another custom opto interrupter 3D printed thing to monitor those. Although I did extend the fingers by gluing some pieces of nickel strip to them. And since this is a bit of a tight space, I decided to put some heat shrink on there just to make sure it didn't scrape up the diodes. The resistors were also a bit tricky to pick, depending on the exact configuration of the opto interrupter, whether it was a shelled one or a stock one. Pick a resistor too weak, and it would basically always be tripped, but pick one too strong, and you wouldn't be able to ever pull it down. So this was mostly decided with trial and error. And of course I needed one for the shift key, so I decided to just use the shift pulley lever for this. Around this time I really began to appreciate how far 3D printing has come. With your calipers in one hand, you can literally design your part, slice it, and then send it to the printer, all from the comfort of your bench. And that very nearly completes the entire keyboard, except for 3 keys, those being the Tab key, margin release, and the EXP key, which I assume means express. I don't know, I didn't read the manual. The margin release and Tab keys were pretty straightforward. I was able to find a good spot for the Tab key on the front, and then for the margin release, the opto interrupter went underneath the bell solenoid mount. The EXP key is really the odd one out. If you push and hold it down all the way, it's connected to this lever, which I showed earlier. It makes the carriage go backwards. But if you only press it a little bit, it doesn't do anything. So it's good for another modifier key. And you just have to manage to put the opto interrupter in such a place that you only have to push it down just a tiny bit to get it to trip. Now we get to move on to the electronics. So I had this board full of MOSFETs I wanted to use, so I salvaged 13 of them and put them on a piece of perf board with an AVR. I did kind of want to use a Pico for this, having not really tried out any of the RP2040 stuff, but the MOSFETs really wanted 5 volts to turn on, and the AVRs are already 5 volt logic. The chip at the lower left is a MAX 232 to convert from TTL serial to RS-232. The interface of choice for any good terminal. It ended up looking not too bad, and the case would still close, which is always good, so now we can move on to the software. Nothing fancy here, I'm just using the Arduino core for the ATmega 1284, mostly because I'm feeling lazy and this is easy, and really I don't need to squeeze every last drop of performance out of this thing. The typewriter may seem fast to us, but its motions are perfectly manageable by even an old slow microcontroller like this one. Now what I probably should have done was have another sensor on the mechanism to detect when it's a good time to activate things. But by dialing in the timing just right, we get something that works pretty well. It is kind of stupid, but it does work. The next hardest part was just finding the character mapping for the ball. So all I did there was print out every character in order and then type what it printed on the paper into the program and use that as a lookup table. There are duplicates in there which you have to watch and remove. Getting into some of the other features, we have the user LED. So again, the typewriter mechanism is still tied together keyboard to print mechanism. So when the LED's on, it's our turn to type, and when it's off, it's the computer's turn to type. Simple. And using RS-232, we have to use flow control, because there's no way the typewriter would be able to keep up with the 1200 baud we're sending it. So I just maintain a buffer inside the AVR and tell the computer when it's good to send a little bit more data. So I can now type every ASCII character there is. So if I do an A, get an A up here, and I get an A over there. If I do a capital A, Shift A, I get a capital A. I can do other things like a carriage return. There it is. And I can do even characters that are not on the keyboard, so like Control G, and that is a bell character, which is also correct. And there are other characters I'd like to type which aren't on the keyboard, and those have special combinations. So for instance, on a normal keyboard, the less than sign is shift and comma, and I can do that on here. And although I get a comma there, I do get a less than sign over here. And then I've also repurposed the 1/4 and 1/2 buttons to something that I'm more likely to normally use. So a half, that prints a tilde, and if I send a tilde, I get a half. Oh, there it is. And then a 1/4 is the vertical pipe, and there's a vertical pipe. There are also characters that I'd like to be able to print on here, but which the ball has no character for. So instance, if I do a less than sign, I actually print 2 characters. I have a left facing parenthesis and a V, because that's what a less than sign looks like. And then if I do a square bracket, we have it with an S for square, a curly bracket, looks like that. A backslash is a slash with a B in it. By holding down the margin release, you can make the printer stop printing and return it to user mode, so you can type something and interrupt whatever the computer's typing. Finally, there's also a problem that the keyboard is not disconnected from the print mechanism, so no matter what I type, it gets printed up here. But computers usually will take your input and then send back what you just typed. So to get around that, there's some software trickery you can do. I just decided to bake it into the firmware. So if I type a key and then the same key comes back within a certain timeout, it won't print it. So printed it twice, but if I do it fast, then it only does it once. And that's the software done. So now we can reassemble the typewriter and move on to the demo section. Notice that we now have 3 cables coming out of the back. There's of course the original power cord. This is the serial cable, which is all ready to plug into a computer serial port. And the third cable is the 12-volt supply for the solenoids, which is this. And again, there's no need for any modification to the case. All we have is the user LED, which sits nicely in the corner over here. Next, I ran a serial cable from my main Linux server over the floor, down the hall, into the shop, and over to the typewriter. So first we'll load in some paper. Now again, since the typewriter and print mechanism are connected, I can't hide my password. But this is just a user account I set up just for this demo, so it's okay. To start off, I could just write hello world or something in text, but instead I'm going to write a C program. And it's at this point where you really understand how all these old Unix programs were really written for a teletype in mind. After all, that was the standard user terminal of the day. This program just prints out a little message and then prints the result of 2 plus 2. And now that we know we typed it correctly, I can now compile it and then run it. And it does seem to be correct. However, I just got this extra underscore in there. I think this is something mechanical with the typewriter. Again, there's a lot of adjustments, lots of moving parts in this, but a couple extra enters gets us back to the prompt. Next, we are using a computer after all, so let's do some math. This is calculating pi using the bench calculator, which is another really old Unix program. Still there on most modern systems, of course. And of course, many teletype users would be familiar with BASIC, especially if you had one of those 70's home computers. BASIC, of course, was a big product of this little startup you might have heard of called Microsoft, and we're getting some more of those weird extra characters inserted here. I'm not sure if this is a BASIC thing or a typewriter thing, but it's kind of annoying. Anyway, I was able to run a short BASIC program counting from 1 to 10, in case you ever forget. Of course, it wouldn't be a 2023 computer project without ChatGPT, and I made a nice little interface in Python so we can use it on our typewriter. ChatGPT's responses can be kind of long and take a long time to print, so instead of printing them directly, we'll just show how many bytes and how many lines we have and then decide if we want to print or not. And there goes another underscore. I promise it worked perfectly before I started filming. And here's a list of the commands we can use. As you can see, it's the full ChatGPT experience. We can move between different chats and create new chats and delete chats. All from the typewriter. And the ChatGPT interface I made should be pretty close to the original, because it's actually a remote control to the normal ChatGPT interface that runs in a browser. Why I decided to do it this way instead of using the API is anyone's guess. Alright, so let's see a couple of responses here. However, ChatGPT doesn't know everything. Here's a trick I like to use that really seems to stump it. So for this next demo, I kind of have no choice but to just do it live because of the way it is. And I'm sure you see what I mean just about now, because everything I type into everything I say into the microphone gets typed onto the typewriter. Which is a pretty neat thing to have happen in your own home. I'm sure when this thing rolled off the assembly line in the 70's, people were wondering if this sort of thing would ever be possible with computers, let alone, running on your own laptop with software that runs locally. So this is a little program called Live Captions, completely open source, runs entirely locally on your laptop, only CPU, no GPU. This is not OpenAI's Whisper. I think that's a little more accurate, but it's meant for like fully recorded stuff, not live stuff like this is doing right now. But yeah, it's a neat app I found and hacked up to output text, which I send to the typewriter. Building it was pretty hard, but eventually managed. Something like this is probably pretty useful if you're hard of hearing, which I certainly am right now, because the typewriter is so noisy I can barely hear anything, even my own voice, and it's kind of difficult to think of things to say. Now, if you've been watching the channel, you'll know of my affinity for putting really old computers on the internet, specifically the part of the internet we call the World Wide Web. That's the part with the web pages and the pictures and videos and stuff. And if you're a connoisseur of internet history, you'll probably know that the earliest web browser, also called World Wide Web, was already graphical. And that's because Tim Berners-Lee and the rest of the team that developed it were using Next cubes, which had a graphical interface. They were kind of like a Macintosh, only with extra Steve Jobs. They were also ridiculously expensive, and not everyone could afford such a luxury in the early 90s, even among the researchers who were the first ones using the internet. And so, as part of the project, the line mode browser was developed, which allowed you to browse the World Wide Web using a text terminal, which was more common. CERN actually tried to recreate this in 2013 with an online simulator, but it doesn't work anymore. I guess that goes to show how the web has evolved over the years. Anyway, the way it worked is you had a screen full of text and it labeled each one of the links, and then you would type the number of the link you wanted and then it would go on to the next page, and that's how you could have a web browser and only text. Now, I actually tried to compile the line mode browser for myself for this project. I went and got the sources and I tried to compile it, and it did compile, but I don't know if it's something I did or maybe it just doesn't work with the modern web anymore, but it loaded a couple pages and then kind of just didn't work anymore, so kind of a dead end there. Although if you really want to see the line mode browser working, it was used as the basis for a number of early web browsers, so here's one of them running on my Macintosh. Of course, there are still more modern text mode browsers like Lynx, but yeah, text mode browsers are still around. The problem with Lynx is that it's meant for a screen, so it can cursor around and draw menus and stuff on top of the screen over and over. Not a typewriter, which can only scroll down and you can't really erase anything. However, if we use the -dump feature with links, we can get a fully rendered page which has all the links labeled, and at the bottom we get a list of references that has the targets for where all the links go. So all I need to do is write a script that kind of cuts off that references section, and then that I can type in the numbers and have it go there. So I'm basically recreating the line mode browser using links as a front end, but now you can access it from a typewriter, although you're just getting these dump sections. You can't actually interact with anything, but it's fine for viewing static web pages. So I'm loading my own web page right now, and again, as with ChatGPT, we don't want to type out the full web page immediately. Instead, we'll show the size of it, and then later we can decide if we want to type it out or not. But before that, I'll show the list of the commands, pretty similar to the ChatGPT thing I made. And then we can type in the number of the link we want and it'll go on to the next page. And then on the next page we can type another number and go to a third page. And like any web browser, it keeps track of your progress, so here's where we've navigated so far. And we can go back if we want to. There's a back command. And then we can visit another page. And even though it's a text browser, on regular links you can click on a picture and it'll open your system's picture viewer. So I implemented one of those for the typewriter. And although it's really low resolution, you can kind of tell what it's supposed to look like. And before we go, we might as well look at a couple other websites. So Retro Hackaday is still around, so let's try that one. Now this did take over 13 minutes to print out. Hacker News was a little bit better, it only took 9 minutes for this one. However, trying to load something like Reddit is absolutely miserable. Several minutes in and we haven't even gotten to the first article. The modern web is simply much too bloated for our typewriter. However, a simple website like CERN's original pages are still around and they load just fine. But if we try to go for something like Wikipedia, just on the first page there's hundreds of links and hundreds of lines to print. So that's about all there is for this project. It's not fast, it's not practical, but it is pretty fun, and that's what really matters. Now you may have seen this project before. It was going around earlier this year. Someone made 3D printed typeballs, and you can put whatever font you want onto a Selectric now, apparently. So of course I had to try some of these out. Although it seems the project has been updated since then, so I'll definitely have to come back to this one. In the meantime, here's the handful of balls I managed to print, and here's what happened.